Thank you. It's a pleasure to be here. Thank the organizers for inviting me. It may help that two of them were co-authors of mine on this enterprise. The object of our study is it depends on the binary expansion of an integer. We consider the powers of 2 that are used to write m, and we count how many powers of 2. That's the sum of digits in base 2. And while Michael was considering 0, 1, 0, 1 as the 2A sequence, we exponentiate that and consider plus or minus 1 to be the 2A sequence, 2A Morse sequence. And it has a nice power series generating function, and but we prefer to work not with power series but with a trigonometric polynomial, which also factors if we stop it at a power of 2. And we are interested in properties of this generating function, particularly various norms of this trigonometric polynomial. We have some trivial estimates. The factor in the product is at most 2 in absolute value, and there are n such factors, so trivially the sup norm is 2 to the n. The coefficient is plus or minus 1, and there are 2 to the n such coefficients, and so by Parseval's identity, the mean square is 2 to the n, and so the 2 norm is 2 to the n over 2, and the 1 norm is trivially less than or equal to the 2 norms. So we have these 3 trivial estimates. Now, Mauduit and Rivat, in their stunning work on primes, the 2A Morse sequence evaluated at primes, needed non-trivial estimates for this. They showed that if you sum the 2A Morse sequence at primes, you get not only little o of pi of x, but actually big O of x to the theta with theta less than 1. And as Michael was explaining, this is using the Vinogradov method for prime number sums coupled with an application of the Vandercorpet differencing on the type 2 sums. But what they needed about the trigonometric polynomial, the underlying generating function, is a non-trivial bound for the sup norm, 2 to the alpha n with alpha less than 1, and a non-trivial bound for the 1 norm, 2 to the beta n with beta less than a half. So I learned about this in 2008, and in 2009 I was lecturing to graduate students in Ann Arbor about this, and it made me wonder, well, what about other norms for this generating function? For example, if you take a 2k power moment of the generating function, you can raise t sub n to the kth power. That will be, t sub n is a trigonometric polynomial with integer coefficients, plus or minus 1. And when you raise it to the kth power, you get a trigonometric polynomial with integer coefficients. And then when you apply Parseval's identity to that, you get an integer. And so we know that this is an integer. And we know that in the case with k equals 1, the mean square is just 2 to the n. And we know that this sequence is growing as a function of n. As a function of n, it's growing at an exponential rate for a fixed k. And I'm thinking, well, what sequences do we know that are integer valued and grow exponentially? Well, I'm thinking linear recurrence sequence. So using maple, I compute some values of the mean square. If there's any message of this talk, it's that one should experiment on the computer and see what is going on with the numbers, because you may discover something that you wouldn't have otherwise realized. There is a technique for detecting when a sequence satisfies a linear recurrence. You form Hankel matrices and ask for the determinants of the Hankel matrices to be 0. This is necessary and sufficient. In particular, for these, the sequence of matrices that you see here extended, this is necessary and sufficient for the sequence to satisfy a linear recurrence of order 2. So we have the sequence, the indices here are 0, 1, 2, 1, 2, 3, 2, 3, 4, and then we start 1, 2, 3, 2, 3, 4, 3, 4, 5, and then we start 2, 3, 4, 3, 4, 5, 4, 5, 6, and so on. And it turns out that these all have determinant 0, which suggests that it's a sequence of that the sequence satisfies a linear recurrence of order 2. And one can solve the linear equations backwards to determine what you think the linear recurrence is. Though this isn't a proof, it's just it just generates a conjecture. Now one can take t sub n to the third power, compute values for that. Maple is very useful for this, and apply Parsifal's identity to that again. Maple can add squares of numbers, and you get another sequence of numbers, and you can form, well, if you form 3 by 3 matrices, you find the determinants are not 0, but if you form 4 by 4 matrices, the determinants are 0 again. And so you conjecture that the mean sixth powers satisfy a linear recurrence of order 3, and you can solve backwards to find out the coefficients of that linear recurrence that seems to be there. And you can do 8th powers and 10th powers and so on, and it seems that the 2kth moment, what I'm calling m sub k here, for any fixed k, satisfies a linear recurrence of order k. So we had an infinite sequence of conjectures with no suggestion or idea how any of these might ever be proved. It was just numerical experimentation with no idea of a proof. But Mauduit and Rivat had quite a few different formulas for recurrences for this trigonometric function, and so if you write down all their formulas on one piece of paper and you stare at it long enough, eventually we came up with a proof that yes, m sub k satisfies a linear recurrence of order k. But it's not a very good proof. If you just look at it and take a frontal attack on it, it depends on the familiar fact that if you have a system of linear equations, homogeneous linear equations, and you have more variables than equations, then it will necessarily have a non-trivial solution. And in our case, the non-trivial solution is precisely the coefficients of the linear recurrence. And so we don't directly have a formula for the coefficients of the linear recurrence. We just know that it's there. But then my co-authors had a further brilliant idea. What we're interested in is the modulus of the generating function, which is a product of twice sine of pi 2 to the rx. And they recalled an earlier piece of work of Fouvre and Mauduit, where such a generating function, or even the 2kth power of it, could be generated by repeatedly applying an operator called q sub k, which is defined this way. And so if you repeat it, if you start with the function that is identically 1, and you apply q sub k, and then q sub k again, and q sub k again, and you do this n times, you get exactly the function whose mean value we are interested in. And so the moments that we were considering, m sub k, is just the integral of the function 1 operated on n times by this operator q sub k. And of course, this integral can be thought of as an inner product of q sub k to the nth operating on 1 the inner product of that with the function that's identically 1. And one can more generally consider what the inner product, if one has two functions f and g with period 1 that are mean square integrable, one could consider what the inner product of qkf with g would look like, and it's precisely this. This is qkf multiplied by g and integrated. And if we replace 2x by u to make a change of variable, so that we take advantage of the fact that f has period 1, it looks like this. But of course, we're now integrating over 2 periods with respect to f. So we could break this up into integral 0 to 1 plus integral 1 to 2, and make the integral 1 to 2 into 0 to 1, and with a translated argument with respect to g. And what we see is that this is actually the inner product of f with some operated version of g. It's p sub k of g is this new animal, which is a function of g. So we have these two operators. I never would have thought to write down such operators. If you don't like them, you can yell at my collaborators. But they act very differently from each other. Q sub k, every time you apply it, it doubles the order of the trigonometric polynomial in question. But p sub k is quite different from that. We can see, because p sub k is the adjoint of f, we can see that we can pass the q sub k over to the other side as p sub k, and we do this n times. And now we find that the moment that we're interested in is actually the integral, the mean value of 1 operated on by p sub k n times. Now, p sub k has an amazing property. If we consider even trigonometric polynomials with period 1 and degree less than k, so this is a vector space of dimension k, there's a certain miracle that happens. P sub k maps this space to itself. It doesn't increase the degree of the trigonometric polynomial. It stays bounded. And of course, one can choose a basis for this vector space. The even powers of sine are a particularly nice basis for the purposes of our calculations. And sine to the 2j, we can see, really is a trigonometric polynomial of degree j. It involves a sum from minus j to j. And cosine to the 2j likewise. And if we apply p sub k to sine to the 2j, this is the result. And we can apply the half-angle formula. We have a sine squared of pi x over 2 and a cosine squared of pi x over 2. If we apply the half-angle formulas to that, we get a 1 minus cosine over 2 to the k plus j and a 1 plus cosine over 2 to the k plus j. Now, if we expand this by the binomial theorem, the odd terms are canceled and the even terms are reinforced. So it looks like this. And this now completes the proof that the operator p sub k maps e sub k to itself, because the cosine to the 2m, as we've already seen, is a trigonometric polynomial of degree m, and m here runs out to j plus k over 2. Now, if j is less than k, then j plus k over 2 is also less than k. It's closer to k, but it's still less. And so as long as we're considering j from 0 up to k minus 1, this will, in the sum here will be over m restricted to up less than k also. Now, this does not, we want to continue this argument one more step, though, because we haven't related the operator of sine of 2 to the sine to the 2j to a linear combination of sine to the same basis that we started with. But to do that, you just write cosine squared is 1 minus sine squared, and you expand now the last factor in the binomial theorem. and invert the order of summation to bring the sum over I outside. And now we have sine to the 2i and multiplied by some coefficient, which doesn't look very pleasant. And this is another case where some numerical experimentation is a good idea, because one wonders, well, could this possibly be written in closed form? It's sort of a mess. And if you evaluate it for, you fix j plus k and you fix I and you get a value, and then you try different values of I and j plus k, and you get a bunch of values. And of course, Maple is perfectly happy to factor these integers, and you find that it's always a product of very small primes. And so that suggests a closed form formula. There's a big power of 2, and you can sort of guess what the power of 2 is, and you take that out, and then things look like factorials, and some primes are missing, and eventually we come up with the hang on. Yeah, okay. So we have I'm sorry, I'm getting ahead of myself. The p sub k acting on sine to the 2j is a linear combination of sines to the 2i with these coefficients. And the point is that ugly sum that occurs in the coefficient can be written in closed form. At least we can conjecture that it has this closed form. Based on it, we can see numerical evidence that it has this form. And, with a little fooling around, once you have a formula to prove, you can find an inductive proof to prove this. So that would suffice. But if you really want to know about identities of this sort, what you do is you ask Dick Askey, who will tell you that this is a special case of the identity of Thue and Vandermonde. So this identity actually goes back to 1303 in China. And Thue also knew Pascal's triangle and the binomial theorem. I mean, this is much deeper in the direction of hypergeometric series than the binomial theorem. And this is, I'm using here the Pockhammer symbol for products of numbers with shifts shifted by 1. And it's a fairly easy exercise to verify that the identity we need is simply an application of the Thue-Vandermonde identity. And so now we have a nice tidy way of writing the coefficients of our matrix, and what we need now is pretty straightforward. The point is that since p sub k is acting on a k-dimensional vector space as a linear operator, its action is described by matrix multiplication. If you choose a basis, then you get we have this matrix A, which is multiplication by A has the effect of applying the operator, and so we have the Cayley-Hamilton theorem. I never used the Cayley-Hamilton theorem before. I never thought I would, actually. Sort of a new experience for me. So the matrix A sub k is a root of the polynomial, of its own characteristic polynomial p sub k. And if we write that out explicitly, we're saying that A sub k to the kth power is this linear combination of lower powers of A sub k. And if we multiply both sides by A sub k to the n minus k, then we find that A sub k to the nth power is a linear combination of the next k lower powers of A sub k. So the sequence of matrices A sub k to the n satisfies this linear recurrence. And of course, this means that if p sub k is the restriction of p sub k tilde is the restriction of p sub k to e sub k, then p sub k to the nth power is just this linear combination of the lower iterates of p sub k. And when we plug that into our formula for the moment, we have p sub k tilde to the nth power, and we can just replace that by the linear combination of the lower iterates of p sub k, and those are just the earlier moments. And so we have a proof of the linear recurrence, the fact that m sub k satisfies a linear recurrence. And this time we're a step ahead of where we were before, because we now know that the coefficients in this linear recurrence are the coefficients. We know when you have a linear recurrence, there's an underlying polynomial, and we now know what that underlying polynomial is. It's the characteristic polynomial of this matrix A sub k, which has the effect of acting the operator P sub k. And that sounds like all good news. I mean, you could wonder why, since we started this in 2009 and it's 2014 now, 5 years later, we still haven't published this work. And the point is that we sort of got stopped here because we suddenly discovered, we have a few more results. The moment is asymptotic to a positive constant C sub k times the spectral radius of A sub k to the nth power. We know that the spectral radius of A sub k is bounded by 3 to the k over 2 plus little o of 1. And we conjecture that this is actually an asymptotic relation. We can compute the trace of A sub k, and it's 3 to the k minus 1 plus big O of 1. And we can compute the determinant of A sub k. It's plus or minus 1 times 2 to the k squared. However, when we did numerics on the matrix A sub k and its characteristic polynomial, we found many more fascinating properties, at least numerically, so we conjecture that the eigenvalues of A sub k are all real. If k is even, we conjecture that half the eigenvalues are positive and half are negative. If k is odd, it has one more positive eigenvalue than negative. The eigenvalues, the large ones, the very largest ones, seem to be asymptotically of this order of magnitude. This is not uniform in I, but the largest one seems to be about 3 to the k over 2, and the next largest one seems to be about the negative of 3 to the k over 4, and so on, geometrically bouncing back and forth. The A sub k seems to be irreducible, but that's not so surprising because most polynomials are irreducible. The eigenvalues of A sub k plus 1 interlace with those of A sub k, at least in our numerical studies they do. And that, of course, that would be the case if there were a mass function with respect to which these are the orthogonal polynomials. So the thing is there a weighting that one could define that with respect to which these would be the orthogonal polynomials, and that would explain why the eigenvalues are real and why they're interlacing and so on. But we can actually prove that there is no such mass function. When there's such a mass function, the orthogonal polynomials satisfy a very specific kind of recurrence, and these polynomials don't satisfy a recurrence of that type. So there is no mass with respect to which these are the orthogonal polynomials. So that's not a way of proving these conjectures. The negative eigenvalues of A sub k, if when you flip them around, replace them by their negatives, they interlace with the positive eigenvalues of A sub k. Now, the problem is we started with one infinite family of conjectures. We proved those, and now we have 6 or 8 infinite families of conjectures, and we have no idea how to prove any of these. At this point, we just give up, and you can take over and prove them for us. Thank you.